Okay, this is a little video to go through some of the basic ideas of equilibria. Okay, we're going to start with this top arrow here. So this is shows that reaction is reversible reaction. This means reaction going in the forward and the backward direction. So reverse reactions go in the forward and backward direction. Linked to that, we need to explain the term dynamic equilibria. So dynamic equilibria is a point that's reached during a reaction where the forward and backward reaction are happening at the same rate. Okay, so here we have got forward and backward reaction happening at the same rate. Now when that happens, once that dynamic equilibrium has been established, what happens then is the concentration of the reactants and products will remain the same. So that also defines a dynamic equilibrium. So reactions going forward and back at the same rate, but also we get a point where the concentration of the reactants and products remains constant. So concentration of reactants and products remains constant. Linked to this, we have to understand Le Chatelier's principle. Le Chatelier's principle says that for a reaction at equilibria, it will oppose any change imposed on it. Okay, so once the equilibrium has been established, a reaction will oppose any change imposed on it. We often refer to this in class as teenager's law. So if we ask it to do something, it will do the exact opposite for us. So for example, if we increased a temperature on a reaction, then because the reaction is at equilibria, what the reaction will try and do according to Le Chatelier's principle. So Le Chatelier's principle says the reaction is going to try and decrease the temperature. It's going to try and oppose that change that we're imposing on it. Okay, so the best way to understand this is to give an example. So underneath here I have got an example. So we have a reaction. I've just made some letters up to help us understand the basic ideas, and this can be applied to any equation at all. Now you always have to be told which direction is endothermic and which direction is exothermic. Let's remind ourselves, endothermic means energy is being taken in, and that means the surroundings will actually become cooler. So that's going to make the surroundings become cooler. Whereas an exothermic reaction, exo is exit, heat exiting, so heat energy exiting, heat energy being given out to the surroundings. Therefore, that's going to cause the surroundings to become hotter. Okay, so we've got these two different reactions taking place. This is at equilibrium, there's my reversible reaction. We've got A and B reacting to make C and D, and then C and D coming back to make A and B. So let's give ourselves a change of condition. If we, in this example, if we increase the temperature, okay, so if we increase the temperature in this reaction, then LCP, Le Chatelier's principle, says that the reaction is going to oppose this, it's going to do the opposite. So it says it's going to lower the temperature. Which way is it going to move to lower the temperature? Well, if you go back to your equation, the equation tells us going in this direction, the forward direction is endothermic, it's going to make it become cooler. So that's how it would lower the temperature. So that means that the equilibrium will move to the right. I'm just going to shorten that down to that, to the right. And why does it do that? Because in that direction, the reaction is endothermic, and that's going to cause it to become cooler. What will that do to this, to the amounts of these? That's going to cause the amount of C and D to increase. So if I just put here in shorthand, amount of C and D is going to increase. Okay. If you look at the opposite, and let's look at pressure, because we can also change pressure on a situation. We need to understand, before we get into the pressure and thinking about pressure, on this side there are 3 moles of A and 2 moles of B. So that gives me 5 moles altogether. And this side we've got 3 of C and 1 of D, 4 moles at the moment, okay? So at this point, this side has higher pressure because there are more moles. This side's pressure is slightly lower because there are less moles on this side. So we get ourselves into a situation where, let's say that we are going to decrease the pressure. Then LCP says the reaction will do the exact opposite. So LCP says it's going to try and increase the pressure. To do that, we'll go back to our equation. To increase pressure, it's going to have to move to the side with more moles, which means the equilibrium is going to move to the left. So equilibrium moves left. Why does it do that? Because there are more moles. We have to always explain why. So there's more moles there. And what will happen then to the amount of C and D? Well, if it's moving this way, the amount of C and D will increase. So C and D starts to decrease. Okay. Now remember, in all of this, we can also help these reactions to work by adding a catalyst. Catalysts work in that they speed up both the forward and backward reaction by the same amount. So they don't affect the position of the equilibrium. The equilibrium isn't going to change in the way it does here, but the speed at which the equilibrium is established, the attainment of it, is far quicker. So it sets up the equilibrium quicker, but it doesn't change the direction when a catalyst is added. Okay, that's the first video on the basics. I'm going to do a second video which goes through this in terms of Haber process and linking these ideas to the Haber process, which you can watch once you've seen the basic one.